Okay, here is this is going to be the final installment in Module 7, which is organic chemistry. And actually, when I started this project, getting these things together, I thought it was going to be pretty straightforward because we're mostly just talking about nomenclature, naming these things, drawing structures, and naming them a little bit about the chemistry. I hadn't banked on the intricacies of organic nomenclature, but if nothing else, you did see a little bit of an introduction to the fact that there is this stuff really can get pretty involved, and that 4-chloro-2-butanone was actually a pretty simple example. There's what I really didn't say is there are actually people who work their job is naming compounds. All right. You have, it's a chemical abstract service. They pretty much, when you come up with a new compound that's complicated, you send it to them and they name it. All right. So just make sure if you write down a name of a compound, just make sure the main thing is make sure it's unambiguous. 4-chlorobutanone and 4-chloro-2-butanone are both unambiguous. So when in doubt, I guess put the numbers in for the positions. Okay. I don't think there are any quirks in this one, but that's what I thought about the last few presentations as well. So we'll see. We're going to talk about carboxylic acids, esters, and amines, actually. We're going to amines and amides. That's in this chapter. And anyway, this is the whole chapter. We're not doing all of this. We're going to be doing amines. We're not going to do amides, really. I am at the very end going to tell you what an amide is, because amides are very important in proteins. All proteins are polypeptide chains, and a peptide bond is an amide bond. So at least I'm going to define it for you. But I'm not going to go much beyond that. Okay. We're talking about oxygen-containing groups, and, well, oxygen and nitrogen. Amines they contain nitrogen. And these things change the properties of these compounds quite a lot. If you take something like, let's take decane, or no, let's take an 18 carbon chain. Okay, octadecane, just straight chain, octadecane. Okay, that by itself, that's an alkane. It's a fairly high molecular weight. It's not very volatile. It will burn. You can get it to burn, but it doesn't really do much chemistry. You put an oxygen group on it. You put a hydroxyl group on it. You put a ketone group on it. You put an aldehyde group on it. You put a double bond in it. You do these things, and there's going to be a handle there for biological systems to work on. All right, like enzymes. We'll talk about it. Well, we're going to get to enzymes. In fact, meet an enzyme. That's this project you're supposed to do. So all these things are what we're talking about are common in chemistry. So carboxylic acids and their derivatives are common in chemistry. The citric acid and the ascorbic acid in the citric acid cycle. Triglycerides are esters of fatty acids, and you now know what an ester is. So what is an acid? A carboxylic acid. You have a carbon atom with a double bond, which you know is a carbonyl. But now instead of two carbon groups attached to it, or a hydrogen there, you now have a hydroxyl group. Those things are acidic. There's reasons why they're acidic. But ethanoic acid, acetic acid, propanoic acid, which is propionic acid, and benzoic acid are all carboxylic acids. If you put these things in water, you're going to be able to measure acidity. They will increase the hydrogen ion concentration. Naming them, it's pretty much the same as it's been, except when you get into the complications like we saw in the last section we worked on. But methane gives you methanoic acid, which we also know as formic acid. Ethane is ethanoic acid, and you've heard of acetic acid already in this course. Well, ethanoic acid is acetic acid. IUPAC, it's ethanoic. And in simple acids, again, you remove the E in alkane in the alkane name and replace it with oic acid. That's all there is to it. Substituents are numbered from the carboxyl bonded to carbon 1. That carboxyl carbon is going to be carbon 1. And in benzoic acids, which is a benzene ring attached to a carboxyl group, the ring carbon attached to the carboxyl group is carbon 1. So you see you have 2,3-dichlorobenzoic acid there. You have 3-methylbutanoic acid. And here's some IUPAC. Actually, these are you would call these the lowest carboxylic acids, the smallest chains, 1, 2, 3, and 4 carbons. Methanoic, ethanoic, propanoic, butanoic, respectively, formic, acetic, propionic, butyric acids. You know of some of these things. You know, the sour taste of vinegar, ethanoic acid, acetic acid. That's what's in vinegar, acetic acid. Formic acid it comes from the Latin word for ant. And red ants have a sting that contains formic acid, so that's a skin irritant, so it can give you a little bit of burn. You find ant stings can be pretty painful. And again, as usual, we're going to be writing the IUPAC names for these things. We're not going to be doing too much with their chemistry, although some of these sidebars, I call them, or they might be called, do give you a little bit of background in the chemistry of these the various compounds we're dealing with. So here's a carboxylic acid. Write the name. All right. Same thing as always. Your longest chain is going to define the name of the acid. So you see there's 1, 2, 3, 4, 5. There's 5 carbons in that chain, including the carboxyl group. The carboxyl group does count in that chain. What else do you have? Well, so it's a pentanoic acid. Pentane, 5 carbons, pentane, that's the parent alkane. You lop off the E, and you add oic acid, so pentanoic acid. And you have a methyl group there, and the methyl group is on the 2 carbons. So this is going to be 2-methyl pentanoic acid. So it's pentanoic acid, 2-methyl pentanoic acid, and you're there. So let's write the IUPAC names of each compound. All right. You've got a 3-carbon chain. So this is going to be a propanoic acid. Propanoic acid. It's from propane, so remove E and add oic acid. The second one, it's benzoic acid. Remember, the benzene ring with the carboxyl group is benzoic acid. You have to remember that. And there's a bromine on it. All right, well, it's going to be a bromobenzoic acid. So we have, and this is going to be a methylpropanoic acid. And they put the numbers down here. It's 2-methylpropanoic acid and 3-bromobenzoic acid. I'm going to, a little bit of an anecdote here, that the acid, this 2-methylpropanoic acid, to me, that methylpropanoic acid is a very innocuous sounding name, but that actual compound also has a common name of isobutyric acid. Now, carbon C4s, okay, butanoic acids, and this one here, 2-methylpropanoic, are, well, the straight chain C4, okay, the butanoic acid is also has a common name of butyric acid. This has isobutyric acid, and I can tell you from experience that these are 2 of the most foul-smelling materials in the universe. They smell bad. They're not the worst I've ever smelled, but they're pretty close to it. So just the 4 carbons, 5 carbons, 6 carbons are really foul-smelling compounds. And then in that range. Benzoic acids, of course, they don't really have much of a smell, but this is 2-methylpropanoic acid and 3-bromobutyric acid. And we need to draw a line angle one for 4-chlorohexanoic acid. So let's do that. Let's get out the whiteboard. You see I was finishing up that other section there. This one looks like it should be easy. And you look at these things, you glance at these things when you're looking through them the first time and you don't see any issues, and then you try to work through them in detail and you find issues. But I don't think there's going to be any issues here. Okay, 4-chlorohexanoic acid. Okay. 4-chlorohexanoic acid. Okay, so what does this tell you? Okay, we know that it's an oic acid. Let me change this. Hexanoic, so there's 6 carbons. And they're asking you for line angle, right? Line angle. They're asking you for line angle. So we really didn't write this. All we really needed to do is do this. Because you see there's going to be 3 of these lines. The way I have actually started writing this is put these down like something like this. And then fill these in. Okay, do the same thing. And it's a hexanoic, but it's a hexanoic acid, so this is going to be CO2H. Okay, it's a hexanoic acid. There's the carbon chain down, and now all I have to do is find the chloro. So this is the 1 carbon, this is the 2 carbon, this is the 3 carbon, this is the 4 carbon. So it's going to be, let's see if we can make this a little bit neater. One, two, three, 4. Okay, so that's Cl. Okay, it should look something like that. And of course, you've got the drawing programs on the Pearson site, which I know they're a little I know it's a little unwieldy, but you can actually come up with a much neater setup than this. And we get that. And that's pretty much what we had. So that's the line angle. And just like that, we're done with section 14.1. So let's move on to section 14.2, where we're going to talk about properties of carboxylic acids. So I'm going to have to switch presentations here, and then I'll get back to you. Okay, I said 14.2, and actually properties of carboxylic acids, and I checked to make sure, and no, it's 14.3. We're not doing that. We're doing 14.1, 14.3, and 14.5. So this should be pretty straightforward. This is going to be a rather long one. This is 22 slides, but it shouldn't be too hard to get through. Okay, we're talking about now another class of compounds, which we call esters. Esters are another common substance common substances in natural products and biological molecules. A lot of the smells of flowers are esters. Some of these things have very nice smells. Salicin is related to aspirin is an ester, so it doesn't really have much of a smell, but there are a lot of esters around. Anyway, acetyl salicylic acid is where, let me draw this thing. They talk about they're talking about the irritating the stomach lining. You have, here, let's draw salicylic acid. Now you see, here's another issue where I was talking about difficulties of nomenclature. This is actually, you can see that can be named as a derivative of a phenol, or it can be, or benzoic acid. So, there's where you have two functional groups there on the same molecule, and then you have to figure out what you want to call this. Well, this is common. This is where common names are nice. Salicylic acid and that erase this. This double bond is to this carbon. That's acetyl salicylic acid. And the problem with salicylic acid is it's rough on the stomach. It's rough on the stomach. It's probably, and if it gets into the into the intestines, it's going to be kind of rough on them, fairly corrosive. So if you make the acetyl salicylic acid, where you see what's happening here, you take this hydroxyl and you're making an ester with it. This is an ester group right here. This is not as bad, although aspirin is also rough on some people's digestive systems, but it's just a little aside there. So the acetyl salicylic acid is less irritating, but still a good pain reliever. And acetaminophen has some similarities, and it too is a pain reliever. Esters are synthesized from the reaction of a carboxylic acid and an alcohol. Okay, and look what's happening there. Carboxylic acid, there's ethanoic acid or acetic acid, and then there is an ester, it's methyl ethanoate or methyl acetate. What you do with these things is you take the carboxylic acid and you add a strong mineral acid, and you mix the carboxylic acid and the alcohol that you want to make the ester with, and you heat it, and you can there's ways where you can force, it's an equilibrium process, but there's ways you can force the equilibrium to the acid. There's ways of doing that. But anyway, these things, they're found in fats and oils. I've said triglycerides are esters, and they're responsible for the aroma and flavor of bananas, oranges, strawberries, and quite a few other things. There's a lot of very, very nice smelling compounds are esters. You have, we didn't say too much about terpenes, which are hydrocarbons. They're primarily hydrocarbons. Some of them are in essential oils of various products, and some of these have very nice smells as well. But esters tend to be, there's not too many bad smelling esters. In fact, I can't think of any really. Anyway, here's what you really do with what I mentioned with an acid and you take the carboxylic acid and the alcohol, and you take a stronger acid. And you remember carboxylic acids like acetic acid, ethanoic acid, they're weak acids. If you take a stronger one, like a little bit of sulfuric acid, you can get this reaction to go, and you can ultimately isolate the desired ester. There's ways of you can get it out of the system. So you can pull. There's ways of if you either remove water from the system or you remove the ester itself from the system, you'll drive that Le Chatelier's principle we talked about. Here's another one. It's propyl acetate. There's that smell of pears. And you can see essentially the same thing going on. It's the same reaction. Ethanoic acid and methanol give you methyl acetate and water. And you see them here. You take ethanoic acid and 1-propanol and make propyl acetate. and water. You see, what's happening with organic chemistry, it's the functional group that does the chemistry. So you can take, I don't know how many carboxylic acids there are. There's probably thousands, millions possible. They're not all very common. The common ones, we're talking about the common ones here: ethanoic acid, propanoic acid, butanoic acid, benzoic acid, and then these smaller alcohols. The hydroxyl group is going to react with the carboxyl group to eliminate water and give you an ester. It doesn't really matter necessarily. It does matter. You want to make if you're making this ester, you want that particular ester, but you're going to make most esters the same way, is the point. So that's one of the beauties of organic chemistry, and one of the complications as well, because the number of possibilities is enormous. Okay, so let's write a balanced equation here. They're asking for balanced equations for the reaction of propanoic acid and methanol in the presence of heat and an acid catalyst. Well, we already have that there? I think we may already have this. Propanoic acid and methanol. Oh no, this was ethanoic acid and propanol. Okay, they're switching. Propanoic acid and methanol. Okay, well let's work this. To erase the whiteboard. Propanoic acid and methanol, methyl alcohol, methanol, that's right. And that's going to methylpropanoate. That's going to be the ester. And it's going to be a H plus and heat. Okay, let's write out propanoic acid, CH3, CH2, CO2H. Remember, we can do that. Or which would you prefer? You want it with the carbonyl? Let's do it with the carbonyl. Let's draw the carbonyl out. Plus CH3OH. Let's see if they added any. Let's just make sure they didn't add any other crazy things. Okay, propanoic acid. Write the balanced equation for reaction of propanoic acid and methanol in the presence of heat in the catalyst. Okay, they want the heat and acid catalyst there. All right, and let's just go back here. Okay, there's none of the other stuff. And that's a solution. We want to show you. You want to see me working it through. Okay, this is going to be the. You're going to have CH3, CH2, CO, CH3 plus water. Now you want a balanced equation, and they said balanced equation. I think it's already balanced. Balanced chemical equation. Yeah, that's what they asked for. So, and this one's already balanced when you look at it. You look at the carbons and the way they're arranged. You have, okay, let's say you have you can look at this, or you can look at the various pieces. Okay, you have the C, CH3, CH2, C double bond O. On that side, you still have that here, and you've got CH3O, that's there, and then you got H2O. Well, let me underline some stuff. Okay, this stays intact. This stays intact. Okay, so that's going to be here and here. And then you have this and this. Oh no, I'm sorry. Let me back off on that. Let's make sure that we know that the oxygen's there. Okay, I'm telling you where the atoms are going. So you have a hydrogen here and an OH here. So there's an H2O. So this thing looks like it's already balanced. Well, they said heat. They say heat there. So H plus and heat. And that should be it. So let's see if I agree with the text. And you see that you didn't really have to do anything with it. You didn't really have to change any coefficients or anything. It was just one of each, and they gave you the four products. So this is a pretty straightforward reaction. And again, you've got these double arrows, meaning it's an equilibrium process. If you've got these things in a pot boiling and reacting, you're going to get an equilibrium mixture. You're going to get only so far into the reaction, and there's just not going to be any more. You're going to have both starting materials and products, in other words, is what you're going to have here. But as I said, there are ways you can force this reaction in different directions. Naming these things, naming esters, it's two words. It's going to be an alkyl part of the alcohol. You're going to the alkyl part of the alcohol. And you're going to have the name, the carboxylate name. In other words, if you have acetic acid, it's acetate, or ethanoic acid, it's going to be ethanoate. So it's going to be that 8 term. And the alcohol, you're going to use a YL in there. So you have, here we have methyl acetate. And so you have ethanoic acid or acetic acid, and methanol is the alcohol. So it's going to be methyl from the alcohol, ethanoate, or methyl acetate. There are also IUPAC in common names. So you see the ones in parentheses are the IUPAC names: ethanoate, propanoate, ethylbenzoate. And now we're going to get into a little history here, a little chemistry linked to health. The Native Americans knew, and I know at least those, they knew that boiling the bark of a willow tree gave you something you could drink that would ease pain, and it turned out it was salicylic acid or some derivative of salicylic acid that did that. There were probably other peoples that knew that too, but that was the story I heard. In 1899, the Bayer Chemical Company, Bayer, it's a German company. I worked for them for 14 years, and it was, we call it Bayer, we say Bayer in the United States, but it's Bayer, it's Bayer. Anyway, they produced an ester of salicylic acid and acetic acid, which I already drew for you, the acetyl salicylic acid, which was less irritating to the stomach than salicylic acid. And they called it aspirin. And I don't quite know where the name came from. And you could easily look it up and probably find a derivation of that. But that really made Bayer made a lot of money for these people. They were mostly, Bayer was into making dyes, things like that. Anyway, there's also people who take a low-dose aspirin daily, which has been found to lower the risk of heart attack and stroke. It can affect blood clotting. It can reduce the tendency of blood to clot, but not enough to really cause any serious problems. Not like hemophilia, for example, which is I think it's a hereditary disease, but that's pretty bad. Then there's wintergreen, methyl salicylate, these are used as ointments, not ointments, as flavorings as well. So if you know where oil of wintergreen comes, if you know what spearmint is, what it tastes like, well, that's methyl salicylate. So it has that mini odor and flavor. It's used in skin ointments. It can pass through the skin, acts as a counter irritant. Notice the salicylic acid skeleton gives you some various analgesic properties. The a lot of well, there's something called Bengay, which has been around for years and years. It was developed in France in the late 1800s, and it has some of these. I think it might have methyl salicylate in it. Okay, so there's quite a few. I mean, there's a lot of esters that have medicinal properties. They act as flavorings. They give nice smells to things and so forth. So let's talk about naming these things now. So let's write the IUPAC name of the following ester. All right, you're given the ester. You need the IUPAC name. So what you do, you connect these things. You write the alkyl name for the alcohol, change acid to 8. Okay, so let's identify the alcohol in that first. Or yeah, the alcohol is the first thing named in the connect box there. C2, there's 2 carbons in there, C2H5. There's 2 carbons in that alcohol. Remember, the alcohol, it's the acid has the double bond on it. The acid has the double bond on it, and the alcohol doesn't have any. It's just got an oxygen on it. So C2, CH2, CH3, that's an ethyl group. C3, a C3 acid. Well, that's propionic or propanoic acid is going to be the acid from that. So it's just going to be ethyl propanoate. Ethyl propanoate is going to be the name. Not a whole lot of, you don't even have to think much about that one. Ethyl, see there's the ethyl there is the carbon chain of the alcohol, and the acid is going to be prop something, so propan something, because it's C3, 3 carbons, so ethyl propanoate. Here's kind of switch things around a little bit. You've got a fairly small acid and a fairly large alcohol. Write the IUPAC name for this following compound, which says pear flavor. If you think back, we actually mentioned that earlier in this lecture. Okay, so the alcohol is propyl alcohol, or 1-propanol, and it's going to be propyl, and the other one is going to be, it's from C2, 2-carbon acid, that's acetic acid, so propyl acetate. So propyl ethanoate, that's the IUPAC name, propyl acetate. I caught myself. I didn't really confuse myself. I lost sight of the fact that I was looking for an IUPAC name, but propyl ethanoate is the IUPAC name for this thing. And we have a few other things here, esters and fruits. I've been mentioning that these things are fruits, perfumes, flowers, and flavors of fruits are due to esters. These things are volatile, so we can smell them. They're soluble in water, so we can taste them. If 4 carbons or something like that, and even maybe a little more than 4, they'll actually make a difference in the flavor. They'll make a difference in the smell. And here's some of the chief ones: propyl ethanoate or propyl acetate, odor of pears. Then there's pentyl ethanoate, pentyl acetate, which is bananas. You see these different species of plants. These different fruits. They have their own little spectrum of esters that they put together for their peculiar flavors. Octyl ethanoate, which is a fairly long alcohol in there, octyl ethanoate or octyl acetate, but that's responsible for that it's in oranges. In pineapples, you have ethyl butanoate. So there's quite a mix. And apricots, pentyl butanoate. There's quite a few of these things. A lot of them are different. They differ a lot from plant to plant, from fruit to fruit, and so forth. Okay, we're getting near the end of this section. Draw the condensed structural formulas for the following compounds: 3-bromobutanoic acid and ethyl propanoate. All right, well, we remembered the, I'll never forget the 4-chloro-2-butanone one. But these should be pretty straightforward. And so let's do 3-bromobutanoic acid and see what we get. I said we did say 3-bromobutanoic acid. Okay, that's correct. So 3-bromobutanoic acid. Let's write this thing down so we don't forget. 3-bromobutanoic acid. Oh, that's right. We're not trying to name this thing. We're just trying to draw the structure. And what kind of structure do we need? We want the condensed structural formulas. Okay, so we're not being asked for the line angle drawing, excuse me. 3-bromobutanoic acid. Okay, condensed structural formula. Well, we have butanoic acid. So we know that we have this thing here on our carbon 1. So this is the 1 carbon. And we have 2, 3, and 4. Okay, so 1, 2, 3, and 4. Let's not draw the lines. We've got this thing. You can see, I hope, that this is a butanoic acid. So that's the carbon skeleton. And we know the carboxylic acid's there. There's your carboxyl group. And now we have 3-bromobutanoic acid. Well, this is the 1 carbon here. So 2 and 3. This is going to be a 3 carbon here. So your bromine is going to be on this here. And you're done. Except you have to fill in it's the condensed structural formula. So you have this. Remember here, now there's this carbon here. It's 2 carbons, a bromine, and only 1 hydrogen. Okay, so don't get yourself caught up in make the mistake of putting CH2 here. Okay, make sure, keep track of how many bonds or how many atoms are attached to carbon, or how many bonds there are to carbon. And this is going to be CH2. And that should be it. Now, well, let's take a look at let's do the other one first. Ethyl propanoate. Ethyl propanoate. Okay, you have the ethyl, the alkyl, or whatever. The alkyl is kind of alkyl, ALKYL, is sort of a generic name for this type of group. So this is ethyl. Well, you know what an ethyl is. So that's going to be the ethyl alcohol is going to be where it comes from. And propanoate. Well, that's propanoate. That's a 3 carbon acid. So let's put the wait a minute here. Condensed structural formula. Remember, this is the acid. The propanoate comes from propanoic acid, which is 3 carbons. So we know that it's going to be like this. So those should be the structures. Now, well, let's take a look at the answer. I might have a comment on the 3-bromobutanoic. Okay, that's pretty much, this is what we wrote down. All right. This is the way you want to write it. There's another way of writing this C8, this bromine here, but you really don't need to know that. We're not going to worry about that. That would just be confusing it too much. So that's section 14.3, esters. It's really not, okay, so far this has been fairly straightforward, and hopefully it'll stay that way. So we're going to move on now to section for 14.5, which I believe is amines. Actually, I don't really need that. 14.5. Let me just check to make sure. 14.5 is amines. Yes, it's going to be amines. And let me switch the. Okay, all these compounds have their peculiar properties. Amines are, I guess you could call them well, they are. I mean, they're all these things are unique, but most organic compounds are, well, amines are basic materials. Okay, these are. You remember ammonia? These, if you look at this structure here, you've got those two nitrogens which have attached to, well, they both have NH bonds. Okay, and a couple of the other two of the other NH bonds have been replaced by bonds to carbon. So these things are basic. They're pretty much the quintessential organic base, and their amines actually show up in a lot of things, and they talk about these things being used in blue dyes, indigo, but the amines show up in amino acids. Amino acids are amines. They're amines and they're acids, and some of them have other functional groups too, which you'll see when we get into proteins. They're derived from ammonia, as I said. It's nitrogen with three single bonds to them, and the bonds are either to hydrogen or carbon, and well, at least one is to carbon, because otherwise it's ammonia. And it's nitrogen attached to one or more alkyl or aromatic groups. We have to be careful here. Remember, there's primary, secondary, and tertiary alcohols. Well, there's also primary, secondary, and tertiary amines, but they're a little different. Remember that the primary alcohol was primary because the carbon to which the hydroxyl group is attached was attached to one other carbon, and secondary because it was attached to two other carbons, and tertiary because it was attached to three other carbons. Primary, secondary, and tertiary amines are defined by how many carbon atoms or carbon groups are attached to the nitrogen atom. If it's one, it's primary; two, secondary; three, tertiary. In that sense, it's similar to the alcohols. So you see here, you have methylamine. I'm giving you the common names right here. There's dimethylamine and trimethylamine. Those are the names of these things. And again, with the primary, secondary, and tertiary amines, they're amines. They have the quintessential properties of amines, but they also have their own each one of those classes has its own peculiarities. And here's some drawings of sort of a model of these things and the structures which you just saw. Ammonia, you see, it doesn't have any organic groups on it, any carbon groups on it. And then you have methylamine, dimethylamine, and trimethylamine. So amines have one or more carbon atoms bonded to the nitrogen atom. The simple amines, named as alkylamines. Remember, we were talking about common names of ethers. This is something similar. And the rules for naming are pretty much the same. You list them in the alphabetical order of the alkyl groups, not the not the di and tri or whatever. They do not count. So ethylamine and there's ethylamine, dimethylamine, and you see right there, ethyl dimethylamine. All right, ethyl comes before methyl in the alphabet, so that di and dimethyl does not matter. Okay, it does not count. So let's write the common names of these things. Classify it as primary, secondary, or tertiary. Okay? Well, A, how many carbon groups are attached to the nitrogen? One. That makes it primary. One carbon group is primary. The second one, you notice there's three carbons attached to nitrogen, so it's tertiary by definition. That's the way we define these things. Now name them. Well, they write a common name. This is not IUPAC. So a 3-carbon alkyl group is propyl. So that's propylamine, and you're done. Now here we have a dimethyl and an ethyl. What comes first in the alphabet? Ethyl comes before methyl. Okay, it's ethyl and methyl. The dimethyl in the di and dimethyl does not matter. So it's going to be ethyl dimethylamine. And you see, it's in its tertiary, as we saw. There are also aromatic amines, and the amine of benzene is named aniline. It's aniline. Not sure where that came from, but there were such things as aniline dyes a long time ago, which gave color to, and they still use them to some extent. So, color to wool, cotton, silk, fiber, blue jeans. So you have aniline, and then again, with aniline, with the basic aniline structure, the 1 carbon is the carbon that carries the amino group, the NH2. So you see the next one, there's 4-bromoaniline, and then you have another thing here. Here's a new wrinkle. Yeah, what you have, they mentioned there with we take the aniline, you take the basic aniline structure, and you have a nitrogen there, and you have a hydrogen, but now you have a methyl group here. Okay, when you have a case where you have some group, like an aniline, where you have an alkyl group attached to nitrogen, it's the N-methyl aniline. Yeah, notice they don't talk about putting the methyl groups here on the ring, because you have toluene, which is a methyl group attached to the benzene ring. You have an aniline with an amino group and phenol. When you start mixing those, you end up with you start having to I'll say with the methyl group. Okay, with a methyl group on, if you put a methyl group on the ring, you no longer have aniline. It's a derivative of it's sort of the term is sort of a mixture of toluene and aniline. It's toluidine is actually what it's called. So you're hopefully not going to get any of those. So anyway, this is N-methyl aniline. You could have, of course, this thing here, which is predictably NN dimethyl aniline. Okay, so just some odds and ends there. Let's go back to here. Where are we going? Go to the next slide. So write the common name of these compounds. Okay, we have, they're both amines, obviously, and one is an aliphatic amine. Well, it's not an aniline, and the other one is it's an aniline. So let's write these. I think you could probably see this. I'm hoping you can see this at this point. You have on an A, it's a tertiary amine. They're not asking you for that, but it's good to recognize that. It's a tertiary amine. There's 3 groups attached to nitrogen. 2 of them are ethyl groups, 2 carbons, and 1 is a methyl. So it's going to be, there's 2 ethyls and 1 methyl. Ethyl comes before methyl in the alphabet. Okay, so it's going to be diethylmethylamine. Okay, diethylmethylamine. Let's just keep that in mind. Maybe write it down, make a note. B is an aniline, and remember what we said? We had the N-methyl aniline. Well, that's an ethyl group there on that nitrogen, so it's going to be N-ethyl aniline. Do we have that? You see, there you are. Line angle formulas of amines. These should be predictable by now. Although in this case, the nitrogen is not part of the carbon chain, but it's the end of one of the bonds. So propylamine is going to be 3 carbons. You're going to have the end of the line. You're going to have 1 angle and the next angle, so it's going to be 3 carbons. Propylamine, it's a primary amine. You do the same thing with secondary amines. Here you have ethylpropylamine. It's secondary. And of course, you fill in with nitrogen whatever's left over with whatever's left over on the available in nitrogen. You don't assume nitrogens on the you don't assume hydrogen atoms on the nitrogen. Okay. So there's diethylmethylamine, which is something like, isn't that one we just did? Diethylmethylamine? Yeah, we just did that one. Okay. So there's that. You show the shapes of the amine molecules with one or more alkyl groups attached. These line angle formulas are showing those with one or more groups. It's we're really using the same conventions for these. We're just adding to the terms we need to use because of the increasing numbers of functional groups. So primary and secondary amines with fewer than 6 carbons are soluble in water. Why? Well, they can form hydrogen bonds with water molecules. Remember, hydrogen bonds can be formed between hydrogens attached to oxygen, fluorine, and nitrogen form hydrogen bonds. So in nitrogen, of course, oxygen and, well, actually fluorine, you're only going to see fluorine attached to hydrogen. The fluorine and fluorine covalently bonded does not give you hydrogen bonding. Fluoride ion does. So it's really not, you're not going to see that very often. But a nitrogen in an amine can engage in hydrogen bonding, even if it's a tertiary amine. It simply cannot use its own hydrogens to form hydrogen bonds because it doesn't have any. So the hydrogen bonds you're going to see in tertiary amines are going to be entirely, like, let's draw the kinds of hydrogen bonds. Okay, if you have, I'm going to take, let's say methylamine here, and it's in water. Let's say it's in water. Okay, so you have, I'm going to draw this. Okay, you can form hydrogen bonds to water this way, and you can also do it this way. All right, when you have a tertiary amine, and that's really what they're saying here, you have these 3 things here. You only have this route, but it can still form hydrogen bonds. Okay, so those are one of the quirks with amines, but still there is the, they can hydrogen bond. So any solubility of amines. What do they say about that here? Well, primary amine, because amines contain a polar NH bond, they can form hydrogen bonds with water. Well, tertiary amines don't have a polar NH bond, but they can still form hydrogen bonds with water from the nitrogen atom. So the smaller amines are soluble because they form hydrogen bonds. They're capable of hydrogen bonding with water, so they are polar. And did they give it? 6 carbons or fewer is really the cutoff there. So amines with more than 6 carbons, again, it's the same thing. The effect of the polar group, in this case an amino group, the nitrogen group, is simply, it's diluted. It's being wiped out. So the molecule on an average is less polar or something like that. So the solubility in water is decreased as you get those larger and larger hydrocarbon chains. So this thing here, which has 6, 7, 8, 9, that's not going to be water soluble. Okay, so which of the following are going to be soluble in water? Well, we remember 2 of them are amines. In fact, you can look at C and you can say, well, C is not soluble. That's a hydrocarbon. That's an alkane. And so that's going to be insoluble. The other 2 are going to be soluble because they are amines and they have less than 6 carbons. So that's going to be the way that one works out. So they're not, A and B are soluble in water, and the other one isn't. Now this is another important part of amine chemistry. They act as bases in water. They can form an ammonium ion. It's a weak base, so ammonia reacts with water to give ammonium ion and hydroxide ion to some small extent. And methylamine, all the amines will do something like this to some extent. And ammonia is probably the strongest base of the amines, but they do behave similarly in that way. And they're the amines. Well, here, one reason you put, I don't know that I agree with this. I put lemon on my fish because it makes it taste better, which maybe it's because it's neutralizing some of the amines in the fish. So it's, I guess, depending on how you look at it, but that's what's happening when you put lemon juice on a piece of fish. You're neutralizing the amines. You're forming these ammonium salts. Okay, we have something like you're taking an acid and you're reacting with a base. Methylamines a base, dimethylamines a base, and if you react it with a strong acid, now in water it doesn't ionize much, but with a strong acid like HCl or well, in lemon juice, what's in lemon juice? It's citric acid, right? Yeah, I think it's citric acid, citrus fruits, but it's acidic, and it's a stronger acid than water, so it's actually going to generate more of that ammonium ion. And of course, in case of HCl, the reaction is going to give you a chloride. And I'm not going to try drawing citric acid from memory at this moment, but I will give you a little bit of extra chemistry here. If you have, say, we saw that we've been told that, let's say, methylamine is a weak base, NH2, and in water you will get a little bit of ionization to the ammonium ion and hydroxide ion, but this does not go very far. So sometimes you see these lines drawn where you got a big line going in the other direction. It's going to be mostly this, but if you put something in a little stronger, and I'll use acetic acid as an example or ethanoic acid, simply because you're going to have citric acid is going to be similar in its chemistry. So if you take acetic acid or ethanoic acid, I'm trying to stay with the IUPAC nomenclature. Here you're going to have a lot more of I don't know where this equilibrium lies. I suspect it's going to be, I suspect it's going to be in this direction. So you're going to have CH3, NH3 plus, which is methylammonium, CH3, CO2 minus. So you're going to try something like that. Okay, you're going to have that ammonium acetate. That's going to go a lot further in the direction of products. And of course, if you're using a real strong acid like hydrochloric acid, it's going to be all the way over. So there's, as you can see, the chemistry of these things will gradually gets more involved as you move along, as you learn more and experience more of this. What's a neutralization reaction? Anyway, that was neutralization of an amine. So you can neutralize an amine with an acid. Properties of the ammonium salts. Remember, see in these here we generated ammonium salts, dimethylammonium chloride and methylammonium chloride. They are actually very useful in drugs. A lot of medications are sold as an ammonium salt before they're used as drugs because they're solids at room temperature. They're soluble in water. They're odorless and well, soluble in body fluids as well. So they're easier to deliver. And we got a couple of examples here. You have ephedrine and diphenylhydramine, which are, they give you the structures here as they're ammonium chloride salts when you're given them. You know, solids are easier to work with than liquids. And with amines, they'll oxidize, they have bad smells, and they're a little tougher to work with. So you make the salt, it's a lot easier to handle, and when it gets into body fluids, there's this equilibrium. Eventually, there's going to be some removal of the HCl. Something will tie up the chloride ion, and then something else will we have bicarbonate buffer in the blood, so you're gonna get that over to the amine, which is going to be the active ingredient. So that's how those things are delivered. And same thing with cocaine. This is it can be, well, I mean, people freebase. It's not a good thing to do. It's not something you want to get involved with. But you hear about crack cocaine. Well, this is what it is. You take cocaine hydrochloride, which is the way most people use it. And I'm not advocating using cocaine, okay? But this is what happens. You have a hydrochloride salt, and you react it with sodium hydroxide, and then what's happening there is that hydrochloride salt is a little less potent, and it takes some time to get to lose the HCl, and that's the same thing's happening here. So, what else do we have? There's alkaloids, which are amines that are found in plants. Some of them are very toxic. Well, cocaine's toxic, really bad for you. Nicotine is addictive, and that's found in cigarette smoke. But some of these things do have uses. They're physiologically active compounds, and in the proper situation, they can be very useful. So there's you see nicotine's an amine. There's you see that ring with the nitrogen in it. There are a lot of other aromatic groups, okay, and you can replace a CH in benzene ring with a nitrogen, and you're going to have something called pyridine. And then also there's, well, you see the 5-carbon ring with nitrogen in it. That's I don't even know what you would call that. I never studied alkaloids. But anyway, you see there's a lot of amines. They do have a lot of uses. A lot of them are biologically active, and they can be used and abused. So then caffeine is another, it's an alkaloid, which is a very common one. It's probably, well, it's an alkaloid, and it does have I forget the term I want to use, but it's a stimulant. It increases alertness, may cause insomnia, and so forth. And you can overdo it. You can overdo caffeine. A lot of people do. But that's another one. And there's morphine and codeine. You notice a lot of drugs that tend to be abused are amines. And but then things like morphine and codeine. Well, codeine is a tremendous cough suppressant, and morphine is useful as a painkiller as well. And they're obtained from the oriental poppy plant, the opium poppy. And so that's really what we have on amines. So closing this off here, we'll look at a learning check. Draw the condensed structural formula or line angle formula if cyclic. Okay, so they want condensed structural formula, line angle if cyclic. So that's a hint that one of these is going to be cyclic. So we have methylpropylamine and 2-chloroaniline. So let's get out the whiteboard and look at this. What I said, methylpropylamine. Okay, we said methylpropylamine. Right away, you should be able to see that this is going to be a secondary amine. Because how many alkyl groups are mentioned? 2. If there were 3, well, you'd have dimethylpropyl, or propyl dimethyl, or trimethyl, or tripropyl, or something like that. So you've only got 2 there. So we know that we have nitrogen. We're gonna 1 hydrogen here, and then we're gonna have CH3 and a propyl group. So that's that one. The other one was a chloroaniline, was it? 2-chloroaniline. 2-chloroaniline. Well, you know what aniline is. Aniline's this thing. And there's no N anything. Okay, there is such a thing as N-chloroaniline, but it would say N-chloroaniline. So there's nothing on the nitrogen here other than hydrogens. And 2, well, this is the 1 carbon here, so this is going to be the 2 carbon. And actually, just to be, get rid of that. You could write it this way as well. Okay, let's see what we get here. Looks like we got it, although I wrote the methylpropylamine in the opposite direction from what they do, but that's okay. And we're done. We're done with Module 7 lecture, and you've got assignments to do. Hopefully I can work through some problems or do some stuff here, and I'm available for questions if you have any. So, and also if you need tutoring, we do have tutors. There are people that do this, and you can go for help to them. So that's it. I'm going to get this thing up onto YouTube. I'm going to get the links to you, and I'm going to sign off for the evening. So good night.